Okay, so today I want to talk about more GR stuff. So I'm bouncing between GR and quantum field theory, and if you want me to focus on one in particular or on one type of example or something like that, you can feel free to go into my Patreon page and make a request there. With that being said, let's go right into this. So this is a lecture on GR. So we've talked so far about covectors and vectors and their corresponding spaces. So covectors and vectors and their spaces. And their spaces. We've also talked about tensors a little bit. Tensors and what they are. They're like maps for these vectors and covectors and for combinations between the two. And in particular, there's a special type of tensor called the metric tensor that we covered. And this metric tensor gives us a notion of distance, or something that we can measure. That's why it's called a metric tensor. And this is a very important object in general relativity and in tensor calculus. We also covered a little bit on the covariant derivative. Covariant derivative and the affine connection. And these are sort of the big boys that we talked about so far. So these are, we sprinkled some more concepts in here, but these are sort of the take-homes that I want to get by so far. Today we're going to be talking about transformations. Transformations of these vectors and covectors. All right, and so I want to motivate this by considering the following. I want to take a look at this object right here, a mu, and we also talked about the realizations, this important realization, which is this d mu dx mu realization of a set of bases that can be applied to functions, right? So we have this a mu, this vector right here with its basis and its components. Right, so say we want to transform this guy into a different coordinate system. Well, we would then, in order to do this, this would be equal to a mu times some transformation. I'll just call the transformation this for right now. So multiplied by some vector, and then d mu multiplied by some matrix. So these are not vectors, these are matrices. Okay, this is kind of a weird way of putting this. I'm sure you've probably seen this as a transformation matrix or a Jacobian. The point, however, is to show that we wanted this guy's being transformed, this guy's being transformed. But here's where the physics comes in. The physics comes in by saying all physics should be the same everywhere. So any vector that I describe anywhere in space should be equal to any other vector in a transformed basis. So we fundamentally want this transformation and this transformation to be inverses of one another. All right. And so we could sort of say this as a definition. We could say, well, this right here is a covariant object right here. And I'm going to say that it transforms, or this is a contravariant object, and I'm going to say that this transforms contravariantly to its basis. Right, so I'm just going to have this be an inverse right here. I'll just make that a little bit nicer. right? And then I'll keep this one the same. And so what's my justification for doing this? Well, again, we want the magnitude, we want these vectors to stay the same and under coordinate transformations, and so therefore these guys have to stay, or this right here this is going to be equal to one vector or unit vector, and if that's the case, then we're going to get that this is equal to a mu d mu. Right? This is sort of just a really rough way of sort of justifying why we use inverses, the inverse of these transformation matrices. But let's get into this a little bit deeper. Let's say now that we want, I'm going to say that d mu right here is going to be equal to dx mu dx mu prime. So our mu prime is in the bottom here. This is a covariant object. Right, it's in the bottom here, and this guy is going to be not two mu's. So we can sort of think of this as this guy's in the bottom, this guy's in the top, so those guys some way cancel. Right? They don't really cancel, but this is how we're going to define this transformation. And then for this transformation, this is a contravariant object. This is a little notion of distance again. Distances are contravariant. And we're going to say that this is equal to dx mu dx mu and dx mu. So these little commas here, or not commas, but these apostrophes here mean this is in the transformed basis. So formed basis. This here is in the transformed basis. This right here is the transformation. This is the transformation. And it's a matrix, transformation matrix. And these guys are in the old basis. So old basis. Like this. This is in the old basis. That. So this is sort of how we read this, right? So these two guys are transformation matrices, and then the old basis is transformed into the new basis. And with that all being said, we could take a look at these guys right here, these transformation matrices, and we can see that they're inverses of each other. And that sort of is what we saw in what I had talked about earlier with regards to being inverses of one another. All right, so this is sort of the fundamental transformation rules that we want to abide by. These can be also understood in terms of e-bases. And so instead of our realization, we can do this simply on an orthogonal basis set. And we just say that this right here is, we're going to call, say, mu nu in E nu. Right, so this right here is just this. This is just in sort of a discrete case. And the hat here means in a transform basis. So this is transform basis. This is the old basis, and this right here is a transformation matrix. We can do the same thing, E new, for a basis like this, and we just say this is going to be the inverse of this guy, so mu new, and then we have E mu. Right, same thing here. So again, these guys right here are just the base, this is just in the discrete case, if you will. Okay. What about tensors? So tensors, so these things, so this is again for this is for a covariant object. So this here is the transformation for a covariant object. Here, I'll write this down like this. This here is the transformation of a covariant object and this is the transformation for a contravariant object. So transformation of a contravariant object. And so these transformation rules are strictly for covariant contravariant objects. However, when we begin to consider tensors, so a tensor, for example, that might look like this: T mu prime nu prime, we'll do lambda prime gamma prime. This is some sort of mixed object, right? This is a mixture between some covariant objects and some contravariant objects. Its basis is going to be d mu prime dx nu, and then dx, these are going to be primed, and then d, no, not d, this is going to be partial gamma, like that. Right, so this is a mixed tensor. It doesn't transform covariantly or contravariantly. It transforms in some very mixed, specific way. And when you read this in textbooks, they often tell you a tensor is something that transforms in a very specific way, right? That's not a very obvious sentence to decipher, right? And we're going to see why, and we're going to sort of decipher why that is the case in a bit here, but we're also going to reveal something about the order of these guys as well when we begin to do this analysis. Okay, so these, right, so where was I here? So we were talking about, let me get my bearings one more time here. Okay, so this here is some tensor that has this this basis right here of the combinations of all the possible combinations of all these different types of basis vectors, and we can we can actually break this up here. This is going to equal, I'm just going to say some constant, or some tensor, not constant, but some tensor components, not in the new basis, but in an old basis, times this guy transformed. So this guy transformed is going to be, well, d mu not in the new basis, and there we're going to have a transformation matrix that looks like this. Let me see here. This is going to be like that because, again, this is going to, yeah, so this is going to sum over here to this guy. These two upper indices are going to sum. And then we're going to be left with a basis, this basis right here. So that's good. And then tensor product. We haven't really gone over the tensor product, I'm realizing right now. I'll save that for another video. We'll just keep in mind again that the tensor product basically, actually I think I did go over the tensor product very briefly. I might go into it deeper. We'll see though. But then this is going to be an inverse matrix, and that's going to be new and a new prime, dx new, that's in the old basis, and then we got two more guys here. We're going to have, let's see here, get another inverse matrix, gamma, and then gamma prime, and then dx, that's not gamma, it's lambda. I don't know, don't listen to me. All right, and then the last one here is going to be this guy. This is going to be not an inverse matrix, and this is going to be gamma like this, not in the old, or in the old basis. All right, so this is our transform. So we have these constants out here. This is our transformed base. This is how we write these guys in full. And this is going to be equal to T mu nu lambda gamma. And then I'm just going to bring these matrices out. And I'm going to have mu like this, and then this one right here, the inverse like that, then another inverse matrix, and that's going to be like that, and then this matrix right here like that, and then we're going to have our bases, and our bases are going to be in the old basis. So dx nu, and then dx lambda, and dx gamma, like that. So this is the basis. So this is the basis. And this here, all of this is this guy right here. So this is equal to this guy right here. I'll encompass all of this like that. Right, so this is how the components of this tensor transform. We need 4 matrices, right? And if we remember, matrices, like if I had matrix, I can actually do this in more detail here. Well, I had matrix A, right? Matrix A and matrix B. These are matrices, so if we remember a little bit of linear algebra, this is not necessarily going to be equal to B times A. So it's not equal to this matrix times A, right? And these two guys are not equal, right? So the order here actually matters, therefore. So depending on which bases are before others and after others, so like this covariant object comes before this contravariant object, right? And so therefore, this transformation comes before this transformation, and we have to apply it in that way, or else we get something that's not necessarily equal to our transformed components, right? So this is why this order matters, right? So we can't do this because of this non-commutativity. T mu gamma, actually I'll just, not gamma, T mu nu lamma gamma, or gamma, is not equal to T mu gamma nu lambda. These two guys are not equal, and that's because of this non-commutativity rule. So, and we place this non-commutativity rule in the context of this the transformation of this tensor, and we have a very, very specific, therefore this is a very specific transformation. Right? So this is why tensors are so important. So a tensor, so to recap, we have some space again, and we have the covector spaces and vector spaces. The covectors are like maps for vectors, and vectors are like maps for covectors. So have some space, and we have vectors. We have a vector space. We have a covector space, and then we can, there's a link between the two, right? The link the link comes in the form of these tensor products. We could take tensor products between these two, and then the maps of the combinations of these two are the tensors, and the tensors or the maps they transform in a very, very specific way, as we've sort of proven in this example, right? So like if I were to take, for example, a tensor that modulates between these two spaces, right? If I have some object, in this space, a mu d mu, and an object in this space, b nu dx nu, then I could take a tensor. I could take a tensor T mu nu that is sort of the combination between these two, and it's a map that takes this is a map that takes two vectors, right? It takes two vectors, one here and one in here, and it produces a real number, right? And we've gone over this stuff before, right? I won't rehash it again, but again, the point here in this video is that these guys right here, these guys transform their transformation rules. Rules are not general. They're not. They can't really be generalized. They're not. They don't transform covariantly. Are not purely covariant or contravariant. Contravariant, A-N-T, like that. They are specific. For this tensor in particular, for this map in particular, its transformation rule goes like this, right? And so it's sort of up to us now to know we can develop these matrices. These guys, they're kind of like Jacobian matrices, right? These guys are kind of like Jacobian matrices. If you haven't come across Jacobian matrices yet, if you're not too familiar with these sort of deeper concepts in linear algebra, perhaps not deeper concepts, but if you're these guys right here, these guys are kind of like Jacobian matrices, and they're but they're matrices, and by virtue of them being matrices, this transformation, therefore, is extremely, extremely specific, right? I'll erase all these guys, and then, but yeah, these guys are very, very specific objects. They transform in very specific ways, and for this example, we've sort of proven that, right? And by virtue of non-commutativity, we've also sort of proven that. So I've beaten this up a lot, and I think I've gotten my point across. So with that being said, we'll move on to the next sort of big guy here in GR, which is geodesics. Geodesics. All right, and then with all of this in our belt or in our toolbox, we will be able to get, start diving deeper into two more important objects. Actually, there's two more important objects that we'll put in our toolbox. We'll put the Riemann curvature tensor and Ricci curvature to understand curvature again. So these are going to be this is going to be our toolbox. And we're going to reach into this toolbox and we're going to start using these guys to generate more interesting objects like the Weil tensor and the spin connection. We've already sort of talked about the spin connection, but we'll go more into it. Spin connection. And with these transformations, I'll put transformations in here too now that we talked about it. Transformations. With these transformations in mind, we can also begin to talk about how we're going to put quantum mechanics into our GR, right? We're going to be able to play a lot with some very abstract ideas. And by playing a lot with these abstract ideas, we're going to find some very interesting mathematical notions and notions within deeper areas of physics to inspire ourselves, I guess. This is sort of, we're getting closer and closer to being able to talk about more advanced topics. But again, I'm beating this up like I want to, so we can really begin to understand how all of this begins to come together. So I hope you enjoy this. If you want to support this sort of work, you can go ahead and subscribe to my channel, and you can go to my Patreon page too, where I'll be posting. And I'm going to be posting, I think, like every 2 days or something like that. And so, and if I don't, that means I'm busy. So, yeah, with that being said, I'll see you guys in the next one.